In this video, we'll carry on with our analyses of the data from the Canadian trial of dietary carbohydrates and diabetes. We've taken a good look at the data now, and we fixed some problems, and we have a good idea about where some relationships may exist. Now we're going to move on to formal inferences so that we can more formally answer our research questions. So looking back at our steps of the process of statistical inquiry, we've made it to the formal analyses. And in this video, we'll carry out some formal tests and interpret the results, covering steps 4 and 5. You'll note that we've mixed step 4 in 2 videos, this one and the last one. We did this because, although we've outlined the statistical process as a sequence of steps, in practice it is often an iterative process, where what you learn from formal analyses causes you to look at the data in new ways, which might be considered preliminary analyses, and then these inform new formal analyses that should be carried out, and so on. Let's start with our primary objective, to compare HbA1c between our 2 diet groups. In our preliminary analyses, we decided to look at the change in HbA1c from baseline to the end of the study, to see if that differed between the low GI and the high GI diet. And you may recall that we noted that the largest observations were in the low GI group. As well, the mean was a little bit higher for the low GI group. But we wondered if that was significant, because there's so much overlap between the 2 boxes in the box plot. So now let's carry out a statistical test. Change in HbA1c is a quantitative variable, and we want to compare 2 groups, the low GI group and the high GI diet group. So we'll test whether the means are the same for the 2 groups. The first step in any statistical test is to state the hypotheses. So what we'll test is our null hypothesis that there's no difference in the means between the 2 groups versus our alternative that there is a difference. Our alternative is a not equal to, or two-sided alternative, because we have no reason to test whether one group is higher or lower than the other diet group. And just to define our notation, mu sub h will stand for the mean of the change in HbA1c for the high GI group, and mu with the subscript L will be the mean change in HbA1c for the low GI group. Our 2 treatment groups, the high GI and the low GI groups, include different people. So this is a 2 independent samples case. And to test whether the means in the 2 groups are equal, we can use the 2 independent samples t-test. We have 2 versions of this test. One in which we pool the variances because we assume that the variances are equal in the 2 groups, and the other when we don't make this assumption, or the unequal variance case. We don't really have any reason to make this extra assumption, so we won't. Although looking at the standard deviation of the 2 groups, they're fairly close. And in situations such as this, the 2 versions of the t-test typically give the same result. Here's the formula for the test statistic for the 2 independent samples t-test, not assuming that the variances are equal. We have all these numbers here that we need to calculate this, except for the sample sizes. Because of the missing values caused by dropouts in the study, we don't have observations for everyone that was recruited, and we have the change in HbA1c for 41 subjects on the high GI diet and 49 on the low GI diet. So plugging in the mean of the high GI group, 0.0038, and the mean of the low GI group, 0.0051, the difference in the means is 0 since we're assuming that they're equal, and dividing by the square root of the variance of the high GI group divided by its sample size plus the variance of the low GI group divided by its sample size, and we get the value of the test statistic, which is about -1. There's lots of round-off error here, so I won't bother giving it more precisely. The Welsh-Satterthwaite approximation for the degrees of freedom is 86.7. So we need to calculate our p-value from a t-distribution with 86.7 degrees of freedom. We can draw this t-distribution. It looks something like this. And we can put on this plot our test statistic of -1. Because we're carrying out a two-sided test, values that are more extreme than what we got include values that are both less than -1 and greater than +1, since those are equally as far from 0. And our p-value is the shaded area in the plot. And using some statistical software, the p-value is about 0.3. 0.3 is a fairly large p-value. So we conclude that our data are consistent with the null hypothesis. And there's no evidence of a difference in the mean change in HbA1c between the high GI and the low GI groups. To give a very complete conclusion, in addition to saying that there's no difference, we could give an estimate of the mean change in each group, and, even better, give a confidence interval for the means of these changes, to give a plausible range of values for them. The formula for a confidence interval for the mean is this, and we have everything we need, except for the t-critical values, which for 95% confidence intervals are 2.02 for the high GI group, where we had a sample size of 41, so 40 degrees of freedom, and 2.01 for the low GI group, where we have 48 degrees of freedom. And you can verify that the confidence intervals are these. Note that the confidence intervals overlap quite a bit. This is to be expected since we didn't see a statistically significant difference between the two groups. Let's move on to our secondary objective now, which was to investigate whether the change in CRP differed between the two diets. We decided that we should look at the log of CRP because of its strong right skew. And we noted that the mean change in CRP was quite negative for the low GI group, indicating that their CRP levels dropped in comparison to the high GI group. So now it's time to test whether that's statistically significant. Again, the log of CRP is a quantitative variable, so we can use a two independent samples t-test to test whether or not the means are equal in the two diet groups, and again we'll work with the unequal variances case of that test. So our null hypothesis is that the means are equal in the high and low GI groups, and the alternative is that they're not equal. We have 41 observations in the high GI group and 49 in the low GI group. For this variable, I won't go through all the details of the calculation, but here's what you need to know so you can calculate it yourself, and you should verify that you get the same answers as what we have here. The Welsh Satterthwaite approximation to the degrees of freedom is about 83.7. When we calculate the test statistic for the two independent samples t-test, we get 2.3. And that gives us a p-value of about 0.02. A small p-value now, so we can conclude that we have evidence that the mean change in the log of CRP differs between the two diet groups. To make that conclusion a little bit more complete, again let's look at the confidence interval for the mean change in the log of CRP for each of the diet groups. Note that for the high GI group, it includes 0. So we can't conclude that there was any change in CRP at all for that group. In contrast, for the low GI group, we have a confidence interval that only includes negative values. So it appears that, indeed, CRP dropped on average for the low GI group. And again, that's a good thing. Lower CRP means less inflammation. So this seems to be a beneficial effect of the low glycemic index diet. Something worth noting is there is a little bit of overlap between these confidence intervals. There seems to be a common fallacy that in order to have statistical significance in the two-sample case, the confidence intervals for the two groups cannot overlap. But that's not true. If the confidence intervals didn't overlap at all, the p-value would be extremely small. but you can still have some overlap in the confidence intervals and have a small enough p-value that you declare the means of the two groups statistically significantly different, as we have here. You may recall from the previous lecture, when we first looked at this box plot of the change in log of CRP between the high GI and the low GI diet, that we noted two outliers, a very large outlier and a very small outlier, both in the low GI diet group. And you may be wondering what effect these outliers have on our analyses. Here are some statistics with the outliers in the data and with these two outliers removed. You'll notice that the mean of the low GI group doesn't change very much, even though means are not resistant to outliers. This is because the large outlier and the low outlier in essence balance each other out. The test statistic is a little bit larger when we don't have the outliers in the data. This happens because without the outliers, the variability in the low GI group is less. And as a result, with the lower variability, we have a little bit more power, so we're more able to detect differences between the groups, and we have a smaller p-value as a result. You may also wonder what would have happened if we hadn't taken this log transformation of CRP. After all, we're carrying out a t-test, and t-tests are extremely robust against departures from the condition of needing normally distributed data. In this case, the p-value would have been 0.12, and we would have made the opposite conclusion. We would have concluded that there was no difference in the means between the diets. So although the t-test is robust, it doesn't work in every situation, and it's important to take a look at the data first. Now let's go back to something else we said we would return to in our data. There were treatment failures. 5 people had to leave the study because they needed to go on medication to control their diabetes. There were still measurements taken on these people before they left, so they weren't necessarily missing values. But we may still be worried about whether or not our treatments contributed to this treatment failure. So let's look at the failures by diet group. Of the 5 failures, we can see that 1 was in the high GI group, and the remaining 4 were in the low GI group. Or looking at this another way, 2.1% of the subjects in the high GI group had a treatment failure, while 7.3%, over 3 times as many, had a treatment failure in the low GI group. So is this an indication that we might have a difference between the two diet groups in treatment failures? Unfortunately, we can't carry out a statistical test to compare these proportions between these two groups using the machinery that we've learned in this class. The problem is that the two-sample test of proportions is not robust enough. Recall that this two-sample test for proportions relies on the central limit theorem. And in a previous lecture, we saw that the central limit theorem needs very large sample sizes for estimating proportions when the actual proportion is close to the limits of 0 or 1. That's the case here. We only have 2 or 7% of failures in each group. So we need larger sample sizes than 48 or 55 in order to have proportions that are approximately normally distributed so that we can use the tests we learned. So what can we say? Is this a surprising difference between the two groups? Think of it this way. Suppose we knew there was going to be 5 treatment failures, and we see that they're distributed between the diets as 1 and 4. If there was no difference between the diets, you'd expect 50-50 chance that these treatment failures would be in either diet. If we flipped a coin 5 times, would you be surprised if you only got 1 head? That's the situation we have here, and because we have such a small number of treatment failures, we can't say if this difference between the two diet groups is meaningful. It could just be due to chance. Another potential issue we saw in our preliminary data analysis was a relationship between the change in HbA1c and BMI. If there is indeed a relationship between these variables, including BMI in a statistical model can help explain some of the unexplained variation. This would allow us to get more precise estimates of what we're interested in, which is the effect of diet. This is another example of control. But this would be using a statistical model to control for the effects of another variable. In order to do this, you need multiple regression models, which allow you to have multiple predictor variables. Unfortunately, we're not covering this in this course, but my motivation in telling you this is to encourage you to keep studying statistics. Here are some other issues that came up in the CCD study, our study of the effect of carbohydrates in diabetes, for which some methods that you might learn in more advanced statistics courses would be useful. The CCD study actually had 3 diet treatment groups, not 2. In order to compare more than 2 means, you need a procedure called analysis of variance. The CCD study also had many secondary outcomes, not just CRP. These included measures of cholesterol such as HDL and LDL, and also included fasting glucose and blood pressure and weight and other variables. Whenever we carry out multiple statistical tests, there's a good chance that we might make a type 1 error. That is, we might find a statistically significant result just by chance. There are different ways to protect yourself against a type 1 error. And again, we're going to have to leave that for your next course. Here's one more issue about the CCD study that you may have guessed. The subjects weren't just measured at baseline, and then left for a year and then measured again. Data were collected on the CCD study subjects multiple times during the year. One of the reasons for doing this was to assess whether the pattern of change in the outcome variables changed over time. To see what I mean by this, imagine one diet in which there was a change right at the beginning of the study, but then it leveled off. But a different diet had a gradual change. They might both end up in the same place, but not in the same way. And it would be interesting to study this. One way to do this is using longitudinal data analysis. Again, a topic for a more advanced statistics course. But even with the elementary methods that we've learned so far, we were able to show the main findings of the study. Here's the title from the main paper published from the study in the American Journal of Clinical Nutrition. You can see that differences among the diets in CRP was found, but not differences in HbA1c or glycated hemoglobin. And that's exactly what we found. Moreover, the CCD study was an experiment. So any changes among the diet groups that we saw can actually be attributed to the diet. We can say that dietary changes do cause changes in CRP. We hope this gives you a taste of the study from the beginning to the end and the importance of statistics in carrying out the study well at every step. And we hope it also gives you some motivation and encouragement to study more statistics.